So in year one, we talked about vectors in 2D. In year two, we learn about vectors in 3D instead. Now 2D and 3D vectors are very similar, but there are some small differences which I'm just going to cover quickly. So in year one, we showed that we could write a vector, let's call this vector v, in column form like this here, where a, the top number, is the x direction and b, the bottom number, is the y direction. In year two, the column vectors now have three numbers instead. A and B are still the x and y direction respectively, but we now have C here as well, which controls the z direction. We showed in year one we could also write this vector v in what we call the ij form, where v is equal to ai plus bj. I is the x direction and j is the y direction. In 3D vectors, it's the exact same, but we now call it the ijk form, where we have this k part added onto the end that controls the z direction. In year one, we also talked about the magnitude of a vector. So if we're talking about vector v, we put these two lines at the side of it like this here to show we're talking about magnitude. We can calculate the magnitude of vector v because it's going to be the square root of a squared plus b squared, where a and b are these x and y directions. It's the exact same in year two with 3D vectors, but we also have this c part which controls the z direction in the square root as well. So essentially, the only difference between 2D and 3D vectors is you always have this c part controlling the z direction added on as well. There's one other slight difference between year one and year two vectors. This doesn't come up that often, but you still need to know it. So in year one, we talked about how to find the angle between a vector and a coordinate axis. Go back to the year one videos if you need a reminder of this, but the way I showed you how to do it is to draw a diagram and then use trigonometry to figure it out. Using that method in 3D vectors is a lot more complicated with a 3D diagram, but luckily there's an easy formula you can use to get this angle instead of using that method. So what we're going to say is if vector v makes an angle with the positive x-axis, and we're going to call this angle theta x because we're talking about the angle with the x-axis, then we can use this formula here to find this angle. So it's cos of this angle theta x is equal to a, which is the component of the x direction, over the magnitude of the vector v, and that's really easy, and then you can just plug this in order to find the angle. It's the same if it was something like if we needed to find the angle with the positive y-axis instead. So rather than calling this theta x, we're going to call this theta y. It's the exact same formula, but now instead of a being in the numerator here, it's now b, which is the y direction component here. And it's the exact same logic if it was the z-axis instead, it would now be c, which is the z direction here. I'll go for an example in a moment plugging values into this formula to show you how it works. But apart from those differences there that we just talked about, everything else about 2D and 3D vectors is the exact same. So for example, let's do a bit of a recap. We talked about in year one, we talked about unit vectors. So for example, if we wanted to find the unit vector of this vector here, v, it would be equal to this vector divided by its magnitude, and we sometimes give it this symbol here with this little sign on top of it like this. This is the exact same between 2D and 3D vectors. This is the way that we figure out unit vectors. Just as well, in year one we talked about parallel vectors. This is the same between 2D and 3D vectors. So we talked about if two vectors are parallel, they're multiples of each other. So what I mean by this is, let's say that we have two vectors, let's call them A and B, and let's say that these two vectors are parallel. What this means is that A is equal to lambda B, where lambda is just a number. So for example, it could be that A is equal to 2b, for example. The point being is that A is a multiple of B, with this lambda just being a number. One more thing that we talked about in year one is that vectors are direction specific. So what do I mean by that? So let's say that we have 2 points A and B. So if we go from A to B in this direction, we have the vector AB. If we go in the other direction, so we go from B 2a, so we'd be going this direction. This would be the vector ba instead. These are not equal to each other, they are negatives of each other. So ab is equal to minus ba. This is what I mean by vectors being direction specific. It matters what direction you're going from, either a to b or b to a. Really quick, something else I just want to recap quickly is the idea of position vectors, because this comes up a lot in exam questions. They really like to ask it. So let's say that we have a graph, and let's say that we have a point on this graph which we're going to call A, and let's say that this has the coordinates 3, 4. The position vector of point A is the vector that goes from the origin to this point A, like this here. So this is going to be the vector OA, and because the coordinates of this point are 3, 4, the vector is going to have the direction 3, 4, like this here. And this example I've done for 2D, but this also works the same position vectors for 3D as well. I just wanted to mention it because we're going to be doing some exam style questions and some past exam questions in this video, and position vectors come up a lot. Okay, so here's just an example question in order to plug some numbers into these formulas and show you how they work. So we're given this vector here, which is called f, and it's 3i minus 4j plus 12k. And we need to firstly find the magnitude of the vector f. So as we talked about, to find the magnitude is equal to a squared plus b squared plus c squared, and then the square root of this, where a, b and c are these numbers here, the x, y and z directions. So therefore the magnitude of f is going to be 3 squared plus minus 4 squared plus 12 squared, and then the square root of this, which when you put this into your calculator is equal to 13. So the magnitude of this vector is 13. Okay, and then for part B, we need to find the angle between the vector f and the positive x-axis. So this is the formulas that we talked about before. So it's the x-axis. So the formula is cos of this angle here, which is theta x, is equal to a, which is this number here in front of I, over the magnitude of f, which we figured out in part A. So therefore cos of this angle is going to be a, which is 3, over the magnitude, which is 13. So therefore, in order to figure out what this angle is, we take the inverse cos of this 3 over 13, which if you put into your calculator, says it wants the answer in degrees, is equal to 76.7 degrees. So that's the angle between this vector here and the positive x-axis. And then for part C, we need to find the unit vector in the direction of vector f. So remember, as we talked about, the unit vector of f is going to be the vector f divided by its magnitude, and we figured out the magnitude is 13. So therefore it's going to be this vector f, which is this 3i minus 4j plus 12k, divided by the magnitude 13. The way you just divide this is you just divide the three coefficients here of I, j and k by this 13. So therefore this unit vector is going to be 3 over 13i minus 4 over 13j plus 12 over 13k, and that's the unit vector. One other thing that's the same between 2D and 3D vectors is how you add and subtract them. So here's an example of this. So we're told that vector A is equal to 6, 3, minus 2, and vector B is equal to minus 2, 1, 1. And we need to firstly find A plus B, and the way that we add 3D vectors, as I said, is the same as 2D vectors. So A plus B would be these two vectors added together like this. And just to recap, if you don't remember, the way that you add vectors is you essentially just treat them row by row. So you kind of do it like this. So it would be 6 plus minus 2, which is going to be 4, and then 3 plus 1, which is going to be 4, and then minus 2 plus 1, which is going to be minus 1. So therefore A plus B is equal to 4, 4, minus 1. Okay, and then for the second part, we need to do A minus B, so it's just going to be this vector minus this vector, and like before, you consider the rows individually. So it's going to be 6 minus minus 2, which is going to be A, and then 3 minus 1, which is 2, and then minus 2 minus 1, which is minus 3. So A minus B is 8, 2, minus 3. And then for part C, we need to find 3 times the vector A. So the way that we just do this is we put a 3 in front of this vector here, A, and then what we do is we multiply each of the terms in this vector by 3. So 3 times 6 is 18, 3 times 3 is 9, and 3 times minus 2 is minus 6. So therefore 3a is equal to 18, 9, minus 6. So we're going to move on to exam questions in one moment. I just want to quickly recap one more thing from year 1 vectors that comes up so much in exam questions, and that's how we use position vectors. So here's a typical question on this. So we're given two vectors, OA and OB. These are both position vectors because they start from the origin O. And we're given these two vectors, and using this, we need to find the vector AB. Now, there's a few ways that you can do questions like this. The way that I always do them is I always draw a diagram in order to help me understand and visualize what's going on in the question. So that's what I've done down here. And one thing that's quite interesting about 3D vectors is I've drawn a 2D diagram down here with the X and Y axes. With 3D vectors, you can actually normally get away with drawing a 2D diagram. You don't need to go through the complexities of drawing a 3D diagram with a Z axis as well. So that's quite nice. It's normally fine to just draw a 2D diagram when you're visualizing the problem. So what I've done on this diagram is I've added the points A and B. It doesn't really matter where the points A and B are with respect to these vectors. I've just drawn them randomly on the graph to visualize the problem. And we have the position vector OA, so this is going from O to A, so this is going to be going in this direction, and we have the position vector of BOB, so this is going to be going in this direction, and we need to find the vector AB, so going from A to B. Now, as we talked about in year 1, the way that we do questions like this and find unknown vectors, so we need to find the vector going from A to B in this direction here. So what we're going to do is, starting from A and going to B, we're going to trace over other vectors that we know. Okay, so we're going to start from A and we're going to go down like this to O in this direction. So this is going to be the vector AO, and then what we're going to do from O, we're going to go up to B in this direction here. So this is going to be the vector OB. So what this means is the vector AB is equal to AO plus OB. Okay, so OB, we know this is given to us in the question, it's this 5 minus 1, 1. AO we don't know, but we do know OA, and as we talked about right at the beginning of the video, one thing that's interesting about vectors is they're direction specific. So what that means is that AO is equal to minus OA. So what we can do is we can just sub out AO here for this minus OA, so it becomes AB is equal to minus OA plus OB, and we know what OA and OB are, so therefore we can just sub these in like I've done here. So it becomes minus, because we have a minus here, remember, this 261 plus 5 minus 1, 1. When you have a minus like this in the front, what we're just going to quickly do is easier, is to switch these two terms around. So it becomes this here, so it now becomes 5 minus 1, 1 minus this 261. So we have this minus in between the two vectors here. Now remember how to subtract vectors. We focus on the individual rows. So it's going to be 5 minus 2, which is 3, minus 1 minus 6, which is minus 7, and 1 minus 1, which is 0. So therefore the vector AB is equal to 3 minus 7, 0. As I said, this comes up a lot in exam questions, stuff like this. Okay, so let's start doing some exam questions, and we'll start with this one here, where we're told that a point A has a position vector 5a plus 3j plus 2k, and we're told that a point B has position vector 2i plus 4j plus ak, where a is a positive integer. And for part A, we just need to firstly show that the magnitude of OA, so the position vector of A, is root 38. So remember, to get the magnitude, we do a squared plus b squared plus c squared, and then take the square root of that, where a, b, and c are the coefficients of I, j, and k. So therefore, the magnitude of OA is going to be the square root of 5 squared plus 3 squared plus 2 squared. If you put this into a calculator, it's equal to root 38. So therefore, the magnitude of the position vector OA is equal to root 38. Okay, and then for part B, we need to find the smallest value of A for which the magnitude of OB is bigger than the magnitude of OA. Okay, so we know the magnitude of OA, we figured that out in part A, it's root 38. What we now need to do is figure out the magnitude of OB. Now we have the position vector of point B, which is this here, 2i plus 4j, and then plus this ak, and a is the value that we're trying to find, the smallest value. So what we can do is figure out the magnitude by doing that the magnitude of OB is equal to the square root of 2 squared plus 4 squared plus a squared, like this here. And then we can simplify this because 2 squared plus 4 squared, so 4 squared is 16, 2 squared is 4, so it's going to be 20. So the magnitude of OB is going to be the square root of 20 plus a squared, okay? So now what we can do, as we now have the magnitude of OB and OA, we can now sub these values into this inequality. So we get that the magnitude of OB, which is the square root of 20 plus a squared, is bigger than the magnitude of OA, which is root 38, okay? And then we can rearrange this in order to make a the subject of the inequality. So we can square both sides, so we get that 20 plus a squared is bigger than 38, and then minus 20 from both sides, we get that a squared is bigger than 18, and then take the square root of both sides, so we get that a is bigger than root 18. Okay, so root 18, if you put it into your calculator, is equal to about 4.24. So what this means is that a is bigger than 4.24. Now the question is asking us to find the smallest value of a for which this inequality is true. An important piece of information here is it tells us that a is a positive integer. Remember, an integer is a whole number, so that means the answer can't be 4.24. It has to be a whole number. So as a has to be bigger than 4.24, we need to find the smallest whole number that is bigger than 4.24, which is 5. So therefore the smallest value of a for which this inequality is true is when a is equal to 5. Okay, so here's another past exam question. This one's quite long, so I've shown the whole thing here, and then when I go through part A and part B, I'll just show those parts on the screen. Okay, so this is quite a long question, so let's break down what's going on, okay? So we're told about a point A that has this position vector here, and we're told about point B that has this position vector here. We're told about another point C that has the position vector AI plus 5j minus 2k, where A is a constant and it's a negative number, it's less than 0. And we're also told about another point D, and the point D is such that the vector AB is equal to the vector BD, and we need to use all this information to find a position vector of D. Okay, so the position vector of D is OD, and for this question what we're going to do is we're going to say that OD is equal to D here, and we're going to use this in our equations. Okay, so like before, let's draw a diagram in order to show what's going on. As I said before, we can draw 2D diagrams a lot of the time to represent 3D problems. So we have these 3 points here, A, B and D. I've actually not included C in this diagram because the point C isn't really relevant to part A. Point C kind of comes in part B, so we're just going to ignore it for now. And what it says is that AB, the vector AB, is equal to BD. So the vector AB, so this is going from A to B like this here, is equal to the vector BD, which is like this here. And essentially they're the same length and they're the same direction, so that's why they're equal like this here. And we need to find the position vector of D. So the position vector of A is OA, like this here, going in this direction. The position vector of B is OB, going in this direction. The position vector of D is OD, and it's going in this direction here. Okay, so this question is reliant on this part here. Okay, so let's first focus on AB. So this is this here, and let's find AB using the position vectors. Okay, so to find AB, we need to go from A to B. So let's first go from A to O. So to do this, we're going to go in this direction, so it's going to be AO, and then we're going to go from O to B, so we're going to be going in this direction, so it's going to be OB, like this here. Okay, so AB is equal to AO plus OB. Okay, we know OB, this is the position vector. We don't know AO, but as we talked about before, vectors are direction specific. So AO is equal to minus OA, like this here. So we've got an equation that AB is equal to minus OA plus OB, and we can use these vectors here, the position vectors, in order to figure this out. So if we plug these in, I know we're given it in the IJK format here. When you're adding and subtracting vectors, I always find it's a lot easier to use the column vector format. So I've just quickly converted them into this format like this here. So we've got minus 2, 3, minus 4, plus 4, minus 2, 3. As we talked about before, when we have something like this, it's quicker to kind of switch these terms around when you have this minus at the front. So therefore it becomes 4 minus 2, 3, minus 2, 3, minus 4. Remember, when we subtract vectors, we focus on the individual rows. So it's going to be 4 minus 2, which is 2, minus 2 minus 3, which is minus 5, and 3 minus minus 4, which is going to be 7. Okay, so this is the vector AB. Okay, so now we're going to focus on the vector BD. Okay, so this is this vector here. So we're going to go from B to D. So we're going to start, we're going to go down like this. So this is going to be the vector BO, and we're going to go from O to D in this direction, so this is going to be the vector OD. We have BO, remember direction specific, so this is equal to minus OB, so therefore BD is equal to minus OB plus OD, like this here. And we can sub in the values, so OB is the position vector of B, which is this here, this 4 minus 2, 3. This OD, we don't know. This is what we're trying to figure out, so we're just going to call this D for now, okay? So we have an equation for AB and BD, and AB and BD are equal to each other. So what we can do is create an equation using this by equaling these two terms equal to each other. So what we can do is we can say that 2 minus 5, 7, which is AB, is equal to this here. And then what we can do is rearrange in order to find D, which is the position vector. So what we're going to do, this minus 4 minus 2, 3, we're going to move this to the other side of the equation to make D the subject. So remember, as we're minusing, this is going to become a plus on this side. So it's going to be that D is equal to 2 minus 5, 7 plus 4 minus 2, 3. Again, focus on the individual rows. So it's going to be 2 plus 4, which is equal to 6, minus 5 plus minus 2, which is equal to minus 7, and 7 plus 3, which is equal to 10. So the position vector of D is equal to 6 minus 7, 10. Okay, so for part B, we're told that the magnitude of the vector AC is equal to 4. And then using that information, we need to find the value of A, with A being this constant here in front of the I in the position vector of C, and we're told that A is a constant and A is less than 0. So let's draw a diagram in order to show what's going on. So with the vector AC, so we have 2 points, A and C, and the vector AC is going to be going from A to C, so it's going to be going in this direction here. We have the position vector of A, which is OA, it's going to be going in this direction, and the position vector of C, OC, which is going to be going in this direction here. So in order to find the magnitude of AC, we need to find the vector AC, and we can do this because, so we need to find this vector here, so we're going to need to go from A to C. So starting going down like this to O, so it's going to be AO like this here, and then going from O to C in this direction, it's going to be OC. So therefore AC is equal to AO plus OC. As we talked about before, vectors are direction specific, so that means that AO is equal to minus OA like this here. So OA is this position vector here, and OC is this position vector here. So therefore we can use this information to sub in these vectors. As I talked about before, when we're adding and subtracting vectors, in my opinion, it's easier to do it in the column vector format, which is what I've done here. So it's going to be minus OA, so it's going to be minus 2, 3, minus 4, plus OC, which is going to be this A5 minus 2. But as we talked about before, when we're doing something like this, we can just switch it around so it becomes this here. So therefore it's this vector minus this vector like this here. Remember, when we're minusing vectors in the column format, just focus on the individual rows. So it's going to be A minus 2, which is going to be A minus 2 at the moment, 5 minus 3, which is equal to 2, and minus 2 minus minus 4, which is equal to 2, okay? So therefore we have the vector AC is equal to a minus 2, 2, 2. So therefore remember the magnitude is these three numbers here squared and added together, and then the square root of this. That's how we find the magnitude of a vector. So therefore the magnitude of AC is going to be equal to these three numbers squared, so a minus 2 squared, like this here, plus 2 squared plus 2 squared, and all of this square rooted. 2 squared is 4, so therefore 4 plus 4 here is going to be equal to 8, so we've got this here, and then this magnitude here, we are told in the question, we're told that this magnitude is equal to 4. So therefore we've got this equation here, that the square root of a minus 2 squared plus 8 is equal to 4, and then we can use this to rearrange in order to find the value of a, okay? So firstly, let's square both sides to get rid of this square root here. So therefore it's going to become a minus 2 squared plus 8, get rid of the square root, and then 4 squared here is going to be 16, and then move this plus 8 onto the other side, so it becomes a minus 2 squared is equal to 8. Then we can square root both sides, so we get that a minus 2 is equal to plus or minus root a. Remember the plus or minus, that's important. Root a is equal to 2 root 2. So that means that a minus 2 is equal to plus or minus 2 root 2. Move this minus 2 onto the other side, so we get that a is equal to 2 plus or minus 2 root 2. So that means there are two possible answers for a. A is equal to 2 plus 2 root 2, or a is equal to 2 minus 2 root 2, okay? So which one is it? Well, key here, we're told that a is a constant, but we're also told that a is less than 0. So a is going to be a negative number. 2 plus 2 root 2 is equal to 4.828, whereas 2 minus 2 root 2 is equal to minus 0.828. So as a has to be a negative number, this here isn't going to be the answer because it's positive, therefore this here is the answer. A is equal to minus 0.828. So this is the value of A. Okay, so here's another past exam question. So we're told about this triangle up here, ABC, and we're told that the vector AB is equal to minus 3i minus 4j minus 5k. So this is the vector going from A to B, so it's going in this direction here. And then we also have the vector BC, which is equal to I plus j plus 4k, so this is going from B to C, so it's going in this direction here. And for part A, we need to find the vector AC, so this is going from A to C, so it's going to be going in this direction here. And this is really easy, we've seen this before. So in order to find this vector here, AC, going in this direction, so we need to start from A. So we're first going to go from A to B in this direction, so this is going to be AB, and we're going to go up from B to C in this direction, so it's going to be plus BC like this here. So AC is equal to AB plus BC, and we have both of these vectors here. So AC is going to be equal to these vectors added together. As I talked about before, when you're adding vectors, I think it's easier to do it in the column vector format like this here. So remember, we focus on the individual rows. So minus 3 plus 1 is equal to minus 2, minus 4 plus 1 is equal to minus 3, and minus 5 plus 4 is equal to minus 1. So therefore the vector AC is equal to minus 2, minus 3, minus 1. Okay, and then for part B, we need to show that cos of ABC is equal to 9 over 10. Okay, so the angle ABC, so ABC, is going to be this angle here. And let's just label this B, okay? So we need to find what this angle is here. Now, because we've got the vectors of all three sides, we've got the vector of AB here, we've got the vector of BC here, and we figured out in part A the vector of AC. What we can do is find the magnitudes of all these vectors and therefore figure out what the lengths of these sides are. So that's what I've done down here. I've used the formula for the magnitude of a vector in order to figure out the magnitudes of the vector AB, BC, and AC. So for AB here, it will be minus 3 squared plus minus 4 squared plus minus 5 squared. For BC here, it will be 1 squared plus 1 squared plus 4 squared. And then for AC here, that we figured out in part A, it's going to be minus 2 squared plus minus 3 squared plus minus 1 squared, and then we square root all of this. If you put all this into your calculator, AB, and the magnitude of AB is equal to 5 root 2, and the magnitude of BC is equal to 3 root 2, and the magnitude of AC is equal to root 14. So what this means is that the magnitude of AB, so this side here, is equal to 5 root 2. So this side here has a length of 5 root 2. BC has a magnitude of 3 root 2, so that means that this side here has a length of 3 root 2. And the magnitude of AC is equal to 14, so that means this side here has a length of root 14. Okay, so let's look at this triangle here. We need to find this angle here, and we have the lengths of all three sides. Now, this is a sign that we can use the cosine rule. This is one of the situations when you have three sides, you need to find an angle, that you can use the cosine rule. We did a video on the cosine rule, so go back to that if you need a reminder. So this here is angle B. So if you remember how to label these sides for the cosine rule, so this side here is opposite the angle B, so this will be side B. Again, go back to the cosine rule if you need a reminder of how to label these sides. So this angle here is going to be angle A, so remember that the side opposite to it is going to be side A, and this angle here is angle C, so therefore this side here is going to be side C. Okay, so remember the cosine rule. I needed to remind it myself because it's been so long since I've made a video on the cosine rule. The cosine rule for an angle is this formula up here, where cos of the angle B is equal to a squared plus c squared minus b squared over 2ac, and we have A, B, and C here. So plug these values into this equation. Here, A is 3 root 2, B is root 14, and C is 5 root 2. And then if you put all of this into your calculator, you get out that cos B is equal to 9 over 10. So B, which is this angle here, ABC, is equal to 9 over 10. So we've proved it. So therefore we have the answer. Okay, so here's another exam question where we're given the points A, B, and C, and we're given the position vectors for them, and we need to use this information in order to find the vector A, B. Okay, so as I've talked about before, I think it's best to draw a diagram for questions like this. So this is the diagram I've drawn here with the points A and B. I haven't worried about point C yet because point C isn't really relevant to part A, it comes in part B. So we have the points A and B, and we know the position vectors of point A and point B. So this is OA, so it's going in this direction, and OB, so it's going in this direction here. And we need to find the vector AB, so going from A to B, so it's going in this direction here. We can find this vector because if we start from A, we go down like this to O, so this is going to be AO, and then we go up from O to B in this direction, so it's going to be OB. So AB is equal to AO plus OB. Remember that vectors are direction specific, so AO is equal to minus OA, and these are the position vectors of A and B, which we have up here, so therefore we can just sub them in like this here. So I've talked about before, when you're adding vectors, I think it's easiest to do it in the column format, like this here. So we have this minus in front of this vector, so if we kind of just swap around these two vectors like this here, so we're subtracting them, it's a lot easier to work with. Remember, when you're subtracting vectors, you just focus on them row by row. So 3 minus 2 is 1, minus 3 minus 5 is minus 8, and minus 4 minus minus 6 is 2. So therefore the vector AB is 1 minus 8, 2. And then for part B, we need to show that quadrilateral OABC is a trapezium. Now, this is a question they've actually asked a few times to do with vectors, and especially 3D vectors, about how you need to show that a certain quadrilateral is a certain type of shape. Now, I've looked through the questions. As far as I can see, there have been 3 shapes that they have asked for in exam questions, in terms of you need to show that a quadrilateral is this shape. And therefore, I'm just going to quickly define what they are, and you might need to remember it going into an exam. And these 3 shapes are a trapezium, a parallelogram, and a rhombus. Okay, so a trapezium is very simple. A trapezium just has a pair of parallel sides. So for example, this side and this side here are parallel. That's the only definition of a trapezium. A parallelogram has 2 pairs of parallel sides. So like with a trapezium, it has 1 pair of parallel sides. But with a trapezium, these 2 sides here are not parallel, whereas here these two sides are also parallel as well. Just another small thing with parallelogram is the pairs of sides are also the same length. So these sides here are the same length and these sides here are the same length. A rhombus is very similar to a parallelogram, except all of the sides are the same length. So with a parallelogram, these two sides are the same length and these two sides are the same length, but these two sides are not the same lengths of each other, if that makes sense. Whereas a rhombus, that is the case. All four of these sides are the same length. A rhombus is actually kind of similar to a square. The only difference is that with a square, you have 90-degree angles. With a rhombus, you don't have that. They're not 90 degrees. Okay, so as I said, for part B, we need to show the quadrilateral OABC is a trapezium. So that means that OABC is going to look something like this here, where one pair of the opposite sides are going to be parallel to each other. Now, in this quadrilateral, that means that two things could be true. It means that either OA and BC are parallel to each other, so that's what I've drawn on this shape here. These two sides are parallel. Or it could mean the opposite, where OC and AB are parallel to each other. This is not how I've drawn the quadrilateral here, but that is another possibility in terms of that these sides could be parallel and these two sides are not. So in order for it to be a trapezium, one of these two statements needs to be true. Now, as in part A, we figured out the vector AB, and we know the vector OC, because it's the position vector here. We know both of these vectors, so let's start with this, is we don't at the moment actually know the vector BC. Okay, so we need to find if OC and AB are parallel to each other. Now, as we talked about before, if two vectors are parallel to each other, it means that they are multiples of each other. So another way of saying this is that the vector OC is equal to lambda AB, where lambda is a constant, so it's going to be something like 2, 3, 4, something like that. The point being is that AB, if you multiply it by a number, is equal to OC. OC is a multiple of AB. So we figured out AB in part A, and the position vector of OC is like this here in column format. And you might be able to already see that these are parallel to each other because they are a multiple. You can see that 1, you've got 2 here, so that's times 2, minus 8, minus 16, that's times 2, 2, 4, that's times 2 there. So an easier way to kind of just show this on paper is if you times this vector here, AB, by 2, like this here, 2 times 1 is 2, 2 times minus 8 is 16, 2 times 2 is 4. So you've got 2 minus 16, 4, which is what this OC vector is up here. So therefore OC is equal to 2 times AB. So therefore this here is true. If you multiply AB by 2, it's OC. So therefore OC and AB are multiples of each other. So therefore OC and AB are parallel. So therefore the quadrilateral OABC is a trapezium because it's got one pair of parallel sides. So this statement down here is true. Now you might be thinking to yourself is that we might need to prove this statement here is not true. So therefore it's only got one pair of parallel sides. Whereas if this statement was also true, it would therefore technically be a parallelogram and not a trapezium. If you figure it out, you do realise that these two sides are not parallel, so therefore it is a trapezium. In the mark scheme, it says that you don't need to do this. It actually says something quite interesting in the mark scheme. It talks about the fact that there's kind of no fixed definition of what a trapezium is, in that some people define a trapezium as only having one pair of parallel sides, where there's other people who define a trapezium as having like at least one pair of parallel sides. So therefore I guess technically you could say in that case a parallelogram is a type of trapezium. It doesn't really matter that much. The point being you don't need to prove this here. You only need to prove this statement here is true, and that will give you the marks. Okay, so here's another past exam question. The last couple of questions that I've done for this video, I would say are on the harder end of the spectrum in terms of the vector questions that they could ask you. So here's an example of one like this. Okay, so for part A, we're told about 3 points, point A, point B, and point C. And we're also given the position vectors for these points. And we're told that given the A, B, C, D, so D is another point, and the points A, B, C, D, when you connect them together, make a parallelogram, we need to find the position vector of point D. So this is going to be the vector O D, where O is the origin. Now, this question here is for 2 marks according to the paper. I think that's really unfair. I don't think that's a fair reflection of how difficult this question is. I think it's probably more like a 4-mark question. This was a specimen paper, so it wasn't like a paper that students actually sat like a formal exam. So therefore, I think maybe if it was like that, that it would more accurately reflect the marks, how difficult the question is. Ignore the 2-mark question is what I'm just trying to say. I think it's probably more like a 4-mark question. Okay, so as I've talked about before, I think the best way to approach questions like these is to draw a diagram. So that's what I've done down here. Okay, so what we've got is we've got the points A, B, C and D, and these connect together to form a parallelogram that I've shown in black. And in red, I've just shown the position vectors. So OA, OB, OC, and OD, like this here. And for part A, we need to find the position vector of point D. So this is this vector here going in this direction, OD. Okay, so let's figure this out using our what we know about vectors and how to find vectors. So we need to find the vector going from O to D. So what we're going to do, there's a few ways you can do this question. What I'm going to do is to go from O to D. Let's go from O to C first, so it's going to be OC, and then from here let's go from C to D, so in this direction here. So what that means is that OD is equal to OC plus CD, like this here. So this is useful to us because we know OC, we're given the position vector of C. However, we don't know what CD is. We don't know what this vector here is. But if you look at a parallelogram and you remember the features of a parallelogram, remember that this line here, so this is BA, so this vector is going to be parallel to CD, and it's also got the same length as CD. So as CD and BA are parallel and the same size, what we can say is that CD, the vector, is equal to BA. Okay, these two vectors are the same. So what we can do with this information here is we can sub out the CD here for BA. So we can say that OD is equal to OC plus BA. And what's useful about this is this BA vector here. What we can do is we can figure out this vector using the same thing that we did for OD. So we need to go from B to A. So in order to do this, what we're going to do is we're going to go down from B to O in this direction here. So this is BO, and then we're going to go up from O to A, like this here. So this is going to be OA. So BA is equal to BO plus OA. And what's useful about this is we know OA, this is the position vector of A. And remember that vectors are direction specific, so BO is going to be equal to OB, and we know what OB is. It's this position vector here. So therefore what we can do is sub in these vectors like this here. As I've talked about before, when you're adding and subtracting vectors, I think it's easier to convert it into the column format. So I've just converted these two vectors into the column format. So we've got minus 4, 3, 3 plus 1, 7, minus 2. As I talked about before, I'm going to swap these two vectors around like this here to put the minus in between them like this here. So we've got 1, 7, minus 2, minus 4, 3, 3. Remember, when you're subtracting vectors, go row by row. So 1 minus 4 is minus 3, 7 minus 3 is 4, and minus 2 minus 3 is minus 5. So therefore the vector BA is equal to minus 3, 4, minus 5. And what we can do is we can sub this in here like this. So we've got the OD is equal to OC, so this is this position vector here. Again, I've converted it into the column form here, and then this is plus BA, which is this vector that we figured out here, so the minus 3, 4, 5. Again, remember, in column form to focus on the individual rows. So 2 plus minus 3 is minus 1, 10 plus 4 is 14, and 9 plus minus 5 is 4. So therefore OD is equal to minus 1, 14, 4. And that's how you get the final answer. Again, I don't think 2 marks is a fair reflection on how hard this question is. I think especially because of this kind of diagram here, it's quite complicated visualizing what's actually going on in this question. But the answer is minus 1, 14, 4. Okay, and then for part B, we're told about a new point, x, and we're told that the vector ax has the same direction as ab, and given that the magnitude of the vector ax is equal to 10 root 2, we need to find the position vector of x. So this is going to be the vector OX, okay? So let's draw a diagram in order to show what's going on here between AX and OX. That's what I've done here. So I've drawn on the points A and X, okay? So we have the vector AX that is going in this direction here. Then we have the position vector of X, which is going from O to X, and then we're also going to have the position vector of A, which is OA, okay? So we need to find OX, okay? So we need to find the vector going from O to X, okay? So if we go in this direction here from O to A, so this is the vector OA, and then if we go from A to X in this direction, we can see that the vector OX is equal to OA plus AX, okay? We know what OA is because we're given this in the question, so we need to find what AX is in order to find out what OX is, okay? So we're told some information about the vector AX. Firstly, we're told it has the same direction as the vector AB. This is essentially another way of saying that they are parallel to each other, AX and AB. So remember, the features that parallel vectors have is the vectors are multiples of each other. So what that means is that the vector AX is equal to lambda AB, where lambda is a number, as a constant, so something like 2, 3, 4, something like that, in which when you multiply it by AB, you get AX. In part A, we figured out the vector BA, which is -3, 4, -5. So therefore the vector AB, remember vectors are direction specific, so AB is going to be minus BA. So we're just going to multiply this vector here by -1, so it becomes 3 minus 4, 5. So AB is equal to 3 minus 4, 5. What's also interesting is we're told the magnitude of the vector AX. We're told it's 10 root 2. So what we could do, as we know the vector AB, what we could do is figure out the magnitude of the vector AB and compare it to the magnitude of AX. So that's what I've done up here. I'm figuring out the the magnitude of the vector AB. Remember, to do this, you square these three numbers, add them together, and then square root that sum. And if you do this, this is equal to 5 root 2. So if you compare this to AX, which is 10 root 2, you can see that the magnitude of AX is 2 times bigger than AB. So that means that the vector AX is 2 times bigger than the vector AB. So therefore lambda here is equal to 2. AX is twice the size of AB. So therefore we can figure out the vector AX by just multiplying this vector AB by 2. So therefore it's going to be AX equal to 2 multiplied by this 3 minus 4, 5. So this is going to be equal to 6 minus 8, 10. So therefore what we can do now is just plug in the values of OA and AX. We know OA is this vector up here, and we figured out AX. Therefore OX, if you sub these vectors in, again I do it in column format to make the vector addition easier. It's going to be this 1, 7 minus 2, which is OA, plus this AX, 6 minus 8, 10. Remember, when you add vectors, you consider the rows individually. 1 plus 6 is 7, 7 plus minus 8 is -1, and -2 plus 10 is 8. So therefore OX, the position vector of X, is equal to 7 minus 1, 8. Okay, so here's another past exam question. So we're told about this figure here, which is a sketch of the triangle OAB. So it's these three coordinates that, when connected, form this triangle. And we're told about another point C such that OC is 2 times OA. So OA is this side here. So C is such that OC is 2 times this vector. I'm going to draw on this diagram in a moment to show you what's going on. And we're told about a point M that is the midpoint of AB, so this line here. And we're told that the straight line that cuts through C and M also cuts OB at the point N. And given that OA is equal to A and OB is equal to B, we need to find what CM is. Okay, so I've drawn on this sketch to show what's going on. So let's start with this part here. So we have this point here, which is C, and point C is such that OC is twice that of OA. So OC, which is this vector here, is twice that of OA. Okay, so that's point C. Now, if we focus on this part here, we're told about point M, so this is this point here, and point M is the midpoint of AB. So this here is the line AB, and M is the midpoint of it. And we're told that there's a line that goes through C and M. So this is this straight line here, and it keeps going, and then it cuts OB. So OB is this line here. It cuts it at the point N, which is what I've drawn on here as well. We're told that OA is equal to A and OB is equal to B. So OA, which is this line here, is equal to A, and OB, which is this line at the bottom, is equal to B. And firstly, for part A, we need to find CM. So this is this vector here, okay? So how do we find this? So we need to go from C to M. So what we're going to do, to go from C to M, we're first going to go from C to A, so CA, and then we're going to go from A to M, so AM. So CM is equal to CA plus AM. Okay, so let's break down each of these vectors to show what's going on individually. Okay, so let's start with CA. So this is this line here. Now remember that vectors are direction specific, so CA is equal to minus AC. So AC is the vector going in this direction. And as we talked about in this line here, OC is equal to twice that of OA. So OC is twice that of OA. So as OA is equal to A, and as OC is twice that of OA, therefore this line here is also going to be equal to A, because they're equal to each other, because OC is twice that of OA. So therefore, as AC is equal to A, CA is going to be equal to minus A, like this here. Okay, so now let's go to AM, which is this line here. Now AM is the midpoint of AB. So what that means is that AM is half that of AB, because it goes up to this midpoint here. Okay, so what we need to do first is we can find AB, and then it'll just be half this. So AB goes from A to B, so we're going to go down like this, so it's going to be AO, and then we're going to go across like this, so it's going to be OB. So AB is equal to AO plus OB. AO is equal to minus OA, and we know that OA and OB are A and B respectively, so that means that this is going to be minus A plus B. So AB is equal to minus A plus B. So that means AM is equal to half of this AB, so half of minus A plus B. Expand the bracket, so it's going to be minus a half A plus a half B. So AM is equal to this here. So we have the values of AM and CA now, so therefore we can just plug this into this here. So therefore CM is going to be equal to minus A, and then minus this half A plus half B. Minus a half A, minus A minus a half A is equal to minus 3 over 2A. So that means that CM is equal to minus 3 over 2A plus a half B. Okay, so for part B, we need to show that the vector ON, so this is this vector down here, we need to show that it can be written as this here. Now in this expression, we have this lambda here, where lambda is a scalar constant. So we don't need to find what lambda is. What we just need to do is there to be this scalar constant in our final answer. Okay, so we need to find ON, so this is the vector going from O to N. So what we can do is, starting from O, we can go up to C, like this here, so OC, and then from C we can go down to N like this, so this is Cn. So therefore ON is equal to OC plus Cn. Okay, OC is easy because we're told that OC is equal to 2 of OA, and OA is equal to A, so OC is equal to 2A. Okay, now Cn, now in part A we figured out what Cm is. This is this minus 3 over 2 plus half B. Cn is just a longer version of Cm. So therefore it's going in the same direction. So therefore Cn is equal to lambda, so this is a scalar constant of cm. So that means that it's going to be in the direction of cm. It's going to be a multiple of cm. It's just going to be a longer version, and that's what this kind of constant here is going to be. It's going to be how much longer it is. Is it 2 times longer, in which case lambda b equals 2? Is it 3 times longer, etc.? Something like that. This is what this scalar constant does. We figured out in part A that cm is equal to this, therefore cn is going to be equal to this lambda multiplied by this minus 3 over 2a plus half b. We can expand this bracket, so it's going to be minus 3 over 2 lambda a plus half lambda b. So this is what cn is equal to. So therefore, subbing these values in for OC and CN, ON is equal to OC is 2a like this here, and then plus CN, so it's going to be this minus 3 over 2 lambda a plus half lambda b. Okay, now this half lambda b, there's no other b terms, so this is fine. This here, what we're going to do is factor out this a as it's present in both of these terms, so it's going to become 2 minus 3 over 2 lambda a like this here, and this here is what they want as the answer. So ON is equal to this here. Okay, and then for part C, we need to prove that the ratio between ON and NB is 2 to 1. So what this means is the line ON, which is this here, and the line NB, which is this here, the ratio between their sizes is 2 to 1. Now, of course, this entire line is OB. So ON plus NB is equal to the entire line, which is OB. We need to prove that the ratio between their two sizes, though, is 2 to 1. Remember, this entire side, OB, is equal to this B here, as it says in the question. Now, I have to be completely honest, this wasn't immediately obvious to me how to solve it. I had to look at the mark scheme, and when I looked at the mark scheme, it does make sense how they did it, but I still think this is a really hard question. So, how to do this basically is if we consider ON, so this is this line here, this is a section of the entire line OB. Obviously, as we said here, the other section is made up of NB. The way that we can say this is that ON, or the vector of ON, is equal to a scalar constant of the entire line OB, where this scalar constant mu is less than 1. It's a fraction. The point of this being, the kind of constant isn't that important. The point I'm trying to say is that ON is going to be a fraction of OB. So this constant here is going to be something like a half, or 2 over 3, or 4 over 5, something like that. The point being is that it's going to be a fraction of the entire line OB, with the other fraction of it being made up of NB here. Now, as OB is equal to B, another way that we can say this is that ON is going to be equal to a fraction of B. Now, when you put it in this context, this is really interesting, because if you look that we got in part A, what we got in part A, we got this expression out here as ON. Now, we can see that we have this B part here, the fraction of B, but we also have this A part here. Now, this shouldn't actually be in the final answer, because you can see that ON is going to be a fraction of B. There shouldn't actually be a part of A here. Remember, A is the vector of OA. This shouldn't actually be in the answer for ON. It should only be this portion here. So what this means is the coefficient of A, which is this 2 minus 3 over 2 lambda, this is going to be equal to 0, because it needs to cancel out and only leave us with ON is equal to something B. Okay, so that means that 2 minus 3 over 2 lambda is equal to 0. Rearrange this, so 2 is equal to 3 over 2 lambda, and then divide both sides by 3 over 2, so that means that lambda is equal to 4 over 3. This is kind of the big part of this question that you need to realise, is this here, that this is equal to 0. And then what we can do now, so this part here is equal to 0, so this part's going to cancel out. And what we can do is we can sub this value of lambda in here to get what ON is. So that means that ON is going to be equal to, remember this part here cancels out, ON is going to be equal to half times lambda, which we know now is 4 over 3 b. Half times 4 over 3 is equal to 2 over 3. So that means that the vector ON is going to be equal to 2 over 3b. As the entirety of OB is equal to B, and as ON plus NB is equal to OB, that means that the rest of this line is going to be made up of NB. So that means that NB is equal to 1 over 3B. When you add these two together, you get the entirety of OB. And you can see that 2 over 3B and 1 over 3B is a 2 to 1 ratio, because 2 over 3 is twice as big as 1 over 3. So therefore, the ratio between ON and NB is 2 to 1. As I said, I think this is quite a hard question, kind of initially realizing this here, but therefore that's how you prove it, that you have this ratio here. Okay, so very finally, there's one more question that I want to go through that they talk about in the textbook, and we covered a very similar example back in year 1 vectors when we were doing 2D vectors. This is essentially the exact same question, but it's translated to a 3D vectors question instead, and I think this is kind of quite a difficult question, kind of the most difficult kind of thing that you could be asked with 3D vectors. So we're given a diagram of a cuboid here that goes from O, A, B, and it goes all the way up to G, and we're given the vectors A, B, and C. And we need to use this information to prove that the diagonals OE and BG bisect each other. So I want to remind you of the definition of what bisect means. So bisect means that two lines intersect into two equal parts. So what that means is if you have these two lines here, so they intersect here, let's say these two lines both have a length of 1. If they bisect, it means this line is split into 1/2 and 1/2, and it's the same with this line here. This is split into 1/2 and 1/2. So we need to prove this. So this is what it's going to look like on the diagram. We have these two diagonals, O, E, and B, G. Okay, now remember, when you're doing a proof, you can't assume the proof, so we cannot assume that they're going to bisect. However, what we can assume is that they're going to intersect, and we're going to say that this is going to happen at a point H here. Remember, the term intersect just means that two lines cross each other at a certain point, and this point we've called H. We're not assuming that they bisect into two equal parts, we're just assuming that they intersect. So now what we're going to do is these two diagonals, we're going to find out what these actually are in terms of the vectors A, B, and C here that the question gives us. Okay, so let's start with the diagonal OE. Okay, and let's use the methods that we've already talked about in vectors in order to find out what this OE vector actually is. So if we start from O, so if we go across to A here in this direction, so this is OA, and then we go up from A to G in this direction, so this is AG, and then we go across from G to E in this direction to reach E. Therefore, we get that OE is equal to OA plus AG plus GE. Okay, so what are these vectors? Well, OA here in this direction, as it shows on the diagram, is A. This AG here going in this direction, we can see that this is parallel to C, and it's also the same length as this OC line. So therefore, this is just going to be C. And this GE line, we can see that it's parallel to this B down here, and it's the same length. So therefore, this GE is going to be B. So therefore, OE is just going to be A plus B plus C. That's what the diagonal OE here is. Okay. Now, if we look at the line OH, and this is going up to where it intersects with the other diagonal, we can see that this is a part of the bigger line OE. So what we can say is that OH is equal to lambda OE, where this lambda is a scalar, it's a number, it's going to be a fraction, it's going to be less than 1 because this is part of the OE line, okay? So therefore the other kind of section of the line is this HE part here, but we're going to say that OH is equal to a scalar of OE, where this is going to be less than 1 because it's a fraction of the OE line, okay? So therefore, if we consider this in the context of OE is equal to ABC, we get that OH is equal to this scalar here, lambda, multiplied by this A plus B plus C. Okay, so now let's focus on the other diagonal. Let's focus on BG. G here. So let's start from B. So let's go up like this. So this is BF, and then let's go across like this. So this is FE, and then let's go down like this. So this is EG. Okay, so therefore BG is equal to BF plus FE plus EG. Okay, so BF here is parallel and the same size as this vector here, C, so therefore BF is going to be C. FE goes across like this here, it's parallel and the same size as A, so therefore this is going to be A. If we look at EG, so EG is parallel to this line here, B, and it's the same size as it, but you can see it's going in the opposite direction, so therefore it's going to be minus B. Okay, so therefore BG is going to be A minus B plus C. A and C are positive, but now it's minus B instead. Okay, so if we now consider BH, so this is this here. So like before, this is a section of the bigger line BG. Okay, so what we're going to say is that BH is equal to a scalar, this is a different scalar, we're going to call it mu, of BG, okay, because BH is a section of the line BG, so mu is going to be a fraction, it's going to be less than 1. So therefore BH is going to be this mu here multiplied by this A minus B plus C. Okay, so now we have these expressions that represent OH, so this is this line here, and BH, so this is this line here. Okay, so now we're going to do something quite interesting. What we're going to do is we're going to say that OH here, there is another way that we can represent OH. What we can do, starting from O, we can go across here to B, so this is OB, and then we can go up to H using BH in this direction. So what we can say is that OH is equal to OB plus BH. Now what's interesting about this is OB is just this B here, and OH we have this expression up here for it, and BH we have this expression up here for it. So what we can do is we can create an equation here by subbing in all these values like this here. So it's OH using this equation here is equal to OB, which is B, and then plus BH, which is this equation here, which we've subbed in like this here. If we expand the brackets here, so we have the lambda and the mu here, what we're going to say is it's going to be lambda A plus lambda B plus lambda C is equal to B plus mu A minus mu B plus mu C. Okay, what we're going to quickly do is we're going to factorize the B from these two terms here. So it's going to be mu A and mu C here. But what it's going to be is we've got B minus mu B. So what we're going to say, if we factorize out B, it's going to be 1 minus mu multiplied by B. What we can do now is we can compare coefficients on both sides of this equation in order to make equations equating lambda and mu. So what we can do here, so we've got this lambda A and this mu A, we've got this lambda B and this 1 minus mu B, and we've got this lambda C and this mu C. So what we can say, if we equate coefficients for A, we can see that lambda is equal to mu. Okay, if we look at the coefficients for B, we can see that lambda is equal to 1 minus mu. Okay, if we equate coefficients for C, we can also see that lambda is equal to mu, which is the same as A, so we don't really need to worry about it. But here we've got this pair of simultaneous equations. Okay, so let's solve these pairs of simultaneous equations in order to find out what lambda and mu are. Okay, so we've got here that lambda is equal to mu. So what we can do here, this mu, we can sub it out for lambda. So what we can say is that lambda is equal to 1 minus lambda, then move this minus lambda onto the other side to get that 2 lambda is equal to 1, and then divide both sides by 2, so we get that lambda is equal to a half, and as lambda is equal to mu, this means that mu will also be equal to a half. So let's consider what these constants actually mean. Let's remind ourselves. Okay, so we said that OH is equal to lambda of OE, so this is, remember, the scalar of OH compared to the whole line of OE. Okay, BH is very similar. Mu is very similar in terms of that BH is equal to mu BG. So BG is this line here, and mu is the fraction of which BH is compared to BG. Okay, so if we sub these values in, we get that OH is equal to half OE and BH is equal to half BG. So what this means is that OH is half this of OE and BH is half this of BG. So that means by just logic that HE will be half of OE and HG will be half of BG, showing that they are halves of each other. Like we showed at the start, they bisect each other, okay, because they're the same value on each side. They're both half of the whole side. So therefore this means that the two diagonals bisect each other. So this means that OE and BG bisect. So maybe you need to do a statement at the end when you do a proof.